Okay. After this we will go on and discuss another character table, but before that let us do something. I am kind of bored of these bases. We are only talking about x, y, z, it is boring. Let us use some other kind of base. We are talking about C2V, right? What is the most well known C2V molecule? Water. That is also a boring answer. Water. Now, what I like to talk about with in what might seem to be a sudden jump from what we are talking about now is normal modes of vibration of water. Do we know what are normal modes of vibration? What are abnormal modes of vibration? If there is normal mode, there has to be some abnormal mode also. So, why are these the only sane modes of vibration, or others are all mad modes, or what? Before getting into all that, let me draw something that everybody knows. Let me draw the 3 normal modes of vibration of water. Okay. What is the first one? Symmetric stretch. What is the meaning of symmetric stretch? The 2 bond lengths become long at the same time and they become short at the same time. So, this is plus phase, this is minus phase. Okay. So, this is plus phase. What will be the minus phase? Both are getting short. Okay. Now, what is the next one? One bond gets elongated and at that time the other bond gets shortened, okay, something like this. The 2 bonds move at 180-degree phase difference with each other, okay. So, if this is the plus phase of that, what will be the minus phase? How can I draw it? The opposite kind of reflection. What is the third one? What is the third mode? Bending, right? Right? Like flying, actually. This is the plus phase. What is the minus phase? What is the minus phase? Right? Plus, minus. Now, what are the symmetry operations? So, maybe I will call this Q1, I will call this Q2, I will call this Q3. So, now see E C2 sigma V dashed. Let us see if I can find out if Q1, Q2, Q3 belong to some symmetry species or not. Symmetric stretch, right? Let me write down the most difficult column. No matter what you do, that first column would better be 1. Okay? So, now we are left with only 6 instead of 9. That is great. If I perform a C2 operation, what happens to Q1? Does it remain the same or does it become negative? Please understand what is plus, what is minus. The whole thing is plus, the whole thing is minus. Okay? So, if you turn by C2, it is true that the 2 hydrogen atoms change places, but now look at the arrows. Now, actually we are looking at the arrows, nothing else. The arrows that are going out still keep going out, right? So, that character is 1. What about sigma V? Where is sigma V? Yes. Okay, this is Z, this is X, and so Y has to be on the other side, perpendicular to the plane of the paper. All right. Sigma V is Zx, sigma V dashed is Yz. Okay. Now tell me, what is the character of sigma V for Q1? Are you all convinced it's 1? What? What about sigma V dash? Sigma V dash is like this, perpendicular. Oh. Plus 1 or minus 1. Now once we understand this, the rest should be cakewalk. See, outgoing arrow, right? If I do this reflection, these two arrows interchange places. Outgoing still remains outgoing. No? Show me. This is the arrow, right? This is the mirror. This is what it is, isn't it? Right? Are we all convinced? This is what we need to understand. Once we understand this, it's life is simple. Do you all agree? It's easy, but it's just that initial visualization might be a little difficult. This is the arrow and this is my plane. When I reflect, this is the arrow. Same direction. It doesn't become the opposite direction. All right? So, will you allow me to write 1? So, see, we call it symmetric stretch, isn't it? Perhaps you know this already. Symmetric stretch is symmetric with respect to everything, with respect to all the symmetry operations that are there in C2V point group. Symmetric stretch means symmetric with respect to everything. All right? Antisymmetric stretch, first one is 1, fine. C2, what happens when I apply C2? Doesn't plus phase become minus phase if I apply C2? That means it is antisymmetric. You have forgotten your name again. What's your name? Yeah. And you? Anup. Anup, you understood? Kamal understood, I can see. Anup, have you understood? Sure? Plus goes to minus, minus goes to plus. Meyak? Understood? Okay, very good. So, will you let me write minus 1 here? Yes. What about sigma V? Sigma V is the molecular plane. With respect to molecular plane, is there any change? No, because it is on the plane, right? So, character is what? Minus 1, plus 1. What about sigma V dashed? That now we understand, minus 1. Ziva? Minus 1?
Yes, sir.
Plus 2? Not plus 2. Okay, what about Q3? Bend. If you apply C2, then what happens? This is plus, this is minus, don't forget. So, if I apply C2, then what happens? Same, 1. If I apply sigma V, same, unless it is out of plane bending or something, and here out of plane bending is not even possible, it has to be symmetric. What about sigma V dashed? 1 or minus 1? 1, okay. So, Q1 and Q3, they both belong to A1, isn't it? A1 symmetry species, totally symmetric, and I don't even need to see the character table for A1, because A1 means character with respect to C2, the principal axis is 1, character with respect to sigma V is also 1. That's all I need. Okay. And what about your what about Q2? What is Q2? B1, why B? because character of the principal axis of symmetry is -1, therefore B, and y1 because character with respect to sigma v is +1. So you see, if you had defined your x and y axes differently, the name would have changed. Okay. So you have to be very clear about how we define our axes. Alright. So this is what B1. Fine. And this is something that is a very common question that people like to ask. Before I go back and talk about the C3V point group, I want to ask once again, what is the meaning of normal mode? Yes? Yes. So normal, not as in opposite of mad, right? Normal not as in opposite of abnormal, normal as in orthonormal. We are talking about orthonormal vectors all the time. So these normal modes means that these are ways of mode means way, right? How it does. So these are modes of motion which do not have contributions in each other. So basically vibration is like a molecular dance, right? The molecules are dancing in different way. So now whoever has learned dancing here, if you remember your initial classes, what was taught? 1, 2, 3, 4, right? All initial dance lessons are 1, 2, 3, 4. What to do with your legs, what to do with your feet, right? Once you are okay with that, then you are taught what to do with your hand, arms. Once you learn that, you are taught how to move your feet a little differently, and then maybe how to move your head differently. And then when the actual dance is performed, the dance is really a linear sum of all these normal modes. I know it is like there is a killing the idea that one has for dance, but that's what it is. Even a human dance is nothing but a superposition of normal modes. So please understand this, molecular vibration is a complex motion. At any given time, water does not have to perform a symmetric stretch, pure symmetric stretch, or a pure bend, or a pure antisymmetric stretch. What it does is a complicated motion. As long as there is no displacement in the center of gravity, it is a pure vibrational motion, right? So if you leave that out and look at even a pure vibrational motion, what you have is really a linear sum of Q1, Q2 and Q3. The molecule dances, but what it uses is these basic ways in which it moves the atoms. This is the meaning of normal modes in a very simple layman's terms. Okay, normal mode is not it is not just the equations. This is the actual meaning of normal mode. So that out of plane rocking that you are saying, that will take place if it is not water, but if it is a CH2 group bound to a molecule, a bigger backbone of a molecule, then you do see out of plane motion there also, there is no problem. But if it is water, then it becomes rotation. Great. Now let us come back to this. This is what we have studied so far, Mulliken symbols. Now I think we can do it. Homework is please practice Mulliken symbols from character tables. I am well within my rights to ask you to give the Mulliken names to some symmetry species that I choose. Which reminds me, before we go to the last part of the discussion. So you have worked out C2V. If you can work out C2V, it is very simple for you to work out C3V also. Let us do that. And the reason why I want to do this is that C3V gives us an example of a two-dimensional irreducible representation. 2D IR to a spectroscopist really means two-dimensional infrared spectroscopy. We are not talking about that. We are talking about two-dimensional irreducible representation. Fine. C3V. How do we proceed? What is the first question we ask? The last question we have on the slide is the first question we ask. How many classes? How many IRs? How many classes? E, then C3, two kinds of C3, and 3 sigma v's, 3 classes, right? Right? So this one class agrees that there are 3 classes. Good. So 3 irreducible representations, right? Gamma 1, gamma 2, gamma 3. All right, Nishit? Question? All right, fine. What do we ask next? What are the dimensionalities? That is the next question, right? Li square equal to h. So the question before the next question is, what is h? 6 or 3? Because h is the number of symmetry operations, please don't forget. E, number 1 E, C3 is number 2 and number 3, C3 plus C3 minus, don't forget. There are 3 planes of symmetry, sigma v. So 1 plus 2 plus 3 is equal to 6, h is equal to 6. So now see, Li square equal to 6, L1 square plus L2 square plus L3 square equal to 6. So what is L1, what is L2, what is L3? One, 1, 2, 1, 2, 1, whatever. So you can write it in many options, in many ways. So since you can write it in many ways, instead of creating a Tower of Babel, it makes sense to decide in which order we will write. We will write the first order, one-dimensional representations first, followed by 2-dimensional representations, followed by 3-dimensional representations, and so on and so forth, if they arise. Okay. So L1 is 1, L2 is 1, L3 is 2, that is how we will write. Convention, nothing else. All right. So now first column, first row is very easy, right? First column is 1, 1, 2 this time. Just don't forget L3 is 2, isn't it? And what we said is that the character of E is equal to the dimensionality, right? In case there is a problem, just think, what is the matrix here? What is the matrix for E in a 2-dimensional representation? 1, 0, 0, 1. So what is the character? 1 plus 1, 2, right? So are we all okay with the fact that this character here is 2? Huh? Fine. First row is always 1, 1. So now see, our job is simpler. We just have to find 4 elements now. How do I do it? How do we do it? By this. So what I do is, you write A, B, C, D once again, right? And then you work it out. Can you work this out? Actually, to start with, work only with gamma 2. Work only with gamma 2. Oh no, maybe not. Work with both. Write down the equations. What do you get? So even here, you can have either plus 1 or minus 1. Right? So what should it be? How many plus 1s, how many minus 1s should it be? Because this has to hold. Sum over r, chi I r, chi j r equal to 0. Now take this as I. Gamma 1 is gamma I, gamma 2 is gamma j. Let us say this is A, this is B. What is the equation you have? 1 plus 2 into 1 into A plus 3 into 1 into B equal to 0, isn't it? Right? So what do I need to do? Coefficient of this, I will write 1 explicitly, multiplied by this character, multiplied by this character, that gives me 1. Then coefficient of C3. Why do I take the coefficient? Because actually what are we working with? We are not working with symmetry elements, we are working with symmetry operations. You have C3 and you have C3 square. Okay. The only reason we write 2C3 is that, as we know already, the symmetry operations in the same class have the same character. We are saving space, time and forests by using less paper, right? So that's why. So, but that does not mean that you are going to keep one and you are not going to keep the other one. You must keep two. So what you have to do is you have to multiply 2 by 1 by a. So what you have is plus 2a. Similarly, here you have 3 multiplied by 1 multiplied by b. So that is plus 3b equal to 0. A is equal to either plus 1 or minus 1. B equal to either plus 1 or minus 1. Now tell me what is A, what is B? Naturally, right? So 1, 1, minus 1. So it is 1, 1, minus 1. I just write it once again. 1, 1, 1, 1, 1, minus 1, E, C3, 2C3, sorry, 3 sigma V. Now here I have 2 already. Now this is x, this is y. How do I get x and y? I will need 2 equations. First multiply these two, then multiply these two. That is the easiest way of going about it. So it is 2 plus 2x plus 3y multiplying gamma 1 and gamma 3, and if you multiply gamma 2 with gamma 3, what do you get? 2, then plus 2x, then louder, minus 3y, and both are equal to 0. Are you all okay with this? And some of us have done this already in CH442 or in other courses elsewhere, but for those who have not done it earlier, are you all okay with this so far? It's simple. So now see, look at the two equations. You have 2 plus 2x, and to that whether you add 3y or whether you subtract 3y, it does not make a difference, it is still 0. What does that mean?
X is minus.
That means y equal to 0. So put y equal to 0. Now 2 plus 2x equal to 0. X equal to minus 1. 1, 1, 1, 1, 1, minus 1, 2 minus 1, 0. Okay. Now the question is, we know what minus 1 is already for one dimensional representation, right? It means antisymmetry, changing sign. What does this minus 1 mean? And then what does the 0 mean? Annihilation? No. If it was annihilation, we would not have written it in the character table. So we'll see what it means. Give me a sec. But before that, let's write the Mulliken symbols. I have written the first one, A1. What will the second one be? Will it be A2 or will it be B1? Why A2? Because character of the principal axis is 1, so A. Character of sigma V is minus 1, so 2, A2. Then is E. Now the thing is this, you could have written E1 or E2 rather, E2, but then you do not have to because there is only one E. So in Mulliken symbol, please remember that we only use superscripts, subscripts, etc. when it is absolutely required. When it is not required, we do not use them always. So do not get confused if you see that this prime and double prime are missing even though you have sigma h. That is there in many cases, but the reason why they are not used is it is not required. Okay. If you have two orthoprobos in the class, you have to say you need another quantum number, right? So maybe use the surname or something. But if you have only one, then you do not need it. So that is what is used. All right. Now let us work out the basis. Almost done. Where does Z belong? Here also Z belongs to the first one, A1, totally symmetric representation. Please don't forget, it's called the totally symmetric representation. The totally symmetric representation can have different Mulliken names though. Here it is A1, somewhere it might be A1 double dashed, sorry, A1 dashed, A1 prime, if you have a horizontal plane of symmetry. It can be A1G if you have a center of inversion. It can be A1 prime G, depending on what other symmetry elements you have. Okay. Now, what about X and Y? Where do they belong? Where would X and Y belong? You are taking C3 as is, C3 along the Z axis. What happens to X and Y? Remember that matrix that we have worked out? Rotation by theta? What was, or rotation by 180 degrees, we had worked that out also. What was that? Minus half, then root 3 by 2, then minus root 3 by 2, minus half again, right? That was the matrix. And what we said at that time is that as the action of C3 along Z direction, we are essentially mixing X with Y. That is why it is a two-dimensional representation. X and Y are getting mixed. X does not remain pure X, Y does not remain pure Y. They mix. And when they mix, that is when your off-diagonal elements become non-zero. And that is when you have more than one-dimensional symmetry species, irreducible representations. It is just not possible to simplify any further. There is no way in which you can apply one of these symmetry operations and leave X as a function of X only. It has to mix with Y. Alright. So that is why. So you can work it out and you will see that X and Y belong to E. And since they belong to E jointly, not by themselves, what we do is we put them in brackets and put a comma between them. That is the notation used for more than one dimensional symmetry species. Right. Now let us come back to that question, what is the meaning of minus 1, what is the meaning of 0? Minus 1, as somebody was saying correctly, is because you are turning by C3, remember the matrix, minus half, forget about off diagonal elements, the next diagonal element is minus half. How did we get that? X dashed is equal to minus half X, right, so on and so forth. So you are adding minus half with minus half and thereby getting this minus 1. So it is important to understand that this minus 1 is not equivalent to that minus 1. In a one dimensional representation, minus 1 means reversal of sign. In a 2-dimensional or 3-dimensional or whatever dimension other than one irreducible representation, minus 1 does not mean a simple reversal of sign. It is merely the sum of the coefficients of the different bases that are there. So even though this is minus 1, that is minus 1, they don't have the same implication. Similarly, what about this? What about this 0? We had worked out these matrices also, right? Sigma V, remember? What was the matrix? As I said correctly, 0, 1, 1, 0 is the matrix. So 0, 1, 1, 0 means what? In the transformed coordinates, the original coordinates do not have any contribution in themselves. So X does not have any contribution in X dash, Y does not have any contribution in Y dash. That is the meaning. Okay. Do you remember that matrix 0, 1, 1, 0? Huh? Yes or no? Huh? I can open it up because all the good thing is all presentations are here, right? So the matrix we had when we applied sigma V to xy was 0, 1, 1, 0. That means what? You write xy, maybe I will write it here. This was the transformation matrix that we had worked out. right. So, what does that mean? X dashed is equal to 0 into x plus 1 into y dashed equal to 1 into x plus 0 into y. That means, see, x does not have any contribution in transformed x. Y, sorry, circle the wrong y. Y does not have any contribution in the transformed y. That is the meaning of this x. Okay, it is not complete annihilation. It is annihilation in this sense, that a coordinate does not contribute to the transformed coordinate, to the transformed form of itself, right.